Let me do a summary first. This chapter only got 4 parts. Fleming's right-hand rule, Faraday's law and Lenz's law, AC generator and transformer. Just need to master these 4 parts for this chapter. So, yeah, today gonna be the review and the quiz. Now, important, right? You must know when to use which rule. So in physics, there's 3 rules. Right-hand grip rule, Fleming's left-hand rule, and Fleming's right-hand rule. Hard part is not about remembering the rules. Hard part is about knowing when to use which rule. Right-hand grip rule, we use it when we want to find the magnetic field of a current. Example over here. Let me test you right now, Rachel. If you have a current going into the page, right? What direction is the magnetic field? Clockwise, right? We use the right-hand grip rule to determine that the magnetic field is in the clockwise direction. Right, Jingri? Okay, so that's when we use right-hand grip rule. The next use case for right-hand grip rule is for solenoid. Example, if we have a coil of wire like this, we always want to use the right-hand grip rule to find where is the north pole, where's the direction of the current flow. So that's the 2 uses of the right-hand grip rule. Next one is Fleming's left-hand rule. Very important, you know when to use Fleming's left-hand rule and Fleming's right-hand rule. We use Fleming's left-hand rule when the current is the one that produces the force. We use Fleming's right-hand rule when the force is the one that produces the current. Right, example over here. Can I ask Cliff, what rule? It's not working. Okay, let's say it's lighting up, right? What rule will you use here? Right-hand rule, why? It's the force that produces the current, that causes it to light up. So we use Fleming's right-hand rule. Okay, so must know when to use each of the rules. Fleming's left-hand rule is also force on a moving particle. Right, come, Jeremy, let me test you right now. If I have an electron moving into a magnetic field that's into the page, what's the direction of the force on the electron? Downwards, right? Because the current is to the left, right? Current is opposite to the movement of the negative charge, right? So the force will be downwards. So that's another case where we use Fleming's left-hand rule. It's for moving particle. Okay, of course we use DC motor, we use Fleming's left-hand rule. AC generator, we use Fleming's right-hand rule. So that's a summary of when to use each of the rules. Right. Next thing is Faraday's law and Lenz's law. Faraday's law, very easy. Induced EMF is proportional to the rate of change of flux. Right? Basically, Faraday's law says that if I push the magnet faster, the flux is bigger. Sorry. If I push the magnet faster, the EMF is bigger. Right? Because the flux change faster. If I push the magnet very slow, the EMF is smaller. So Faraday's law says that the faster the change in flux, the bigger the induced EMF. Right, that's Faraday's law. Maybe you can just write down as a note. What this means basically is that faster change in flux gives me the bigger induced EMF. Now, Lenz's law says that the direction of the induced current opposes the change in magnetic flux. So Lenz's law basically says that okay, I thought they were coming. No, Lenz's law says that there's a ghost called Lenz, right? This Lenz guy, he always wants to oppose the motion. Whenever there's an induced EMF, the ghost will try to oppose the motion. Right, so when I push the magnet towards the coil, Jingyan, what do you think Lenz will try to do? Lenz will try to repel the magnet, right? Lenz always wants to oppose the motion. What kind of pole is going to form on the left side? South pole, north pole. Then you use your right-hand grip rule to find the current flow. So do you think the galvanometer will deflect to the left or the right? Yeah. Right, so right-hand grip rule, like this, the current will flow in this way. If we trace out the current is going to flow like this, and deflect to the left side. Right, Lewis? Okay, of course, when we pull away the magnet, what does lens wants to do? Lens wants to attract back the magnet. Lens wants to oppose the motion. So lens will form a north pole, south pole. Right-hand grip rule, the current will flow this way. Right, so that's how to do lens law questions. So actually, right, come, Zachary, can you tell me, Faraday's law, in one word, Faraday's law gives me the what of the current, and Lenz's law gives me the what of the current. Lenz's law gives us the direction of the current. How about Faraday's law? Amount, right? Or kind of physics, sophisticated a bit. What's the magnitude? Yeah. Faraday's law tells us the magnitude of the current. Last thing about this diagram, right, is maybe Alexa, can I ask you, what happens if the magnet, like if I continuously push in and pull away the magnet, what's going to happen? Okay, so I push in the magnet is a south pole, right? When I pull away the magnet, it's a north pole. What's going to happen when I like keep pushing and pulling it away? Yeah, the poles will keep changing, right? The poles will keep changing. As a result, the current will keep reversing. So it will form an alternating current. Means that the current keeps changing direction.
Isn't that an
AC motor.
No, AC
Generator. This one, is it?
Yeah, like because it changes. Right.
Yeah. So it will form an AC output. Right, next thing is the AC generator. We need to know how to understand this. First of all, right, why I draw this windmill?
This is the force.
It's the force, right? So you're got to be clear on this. The AC generator does not spin on its own. Right? The AC generator does not spin on its own. There's an external force that is causing the coil to spin around. That's why I draw the windmill over here. So make a note that the AC generator, there's an external force causing the coil to spin. Right, there's some guy literally, like he's turning the AC generator. It doesn't spin on its own. So first thing for AC generator is you all must understand that this side is always connected to this side below, and this side is always connected to this side. Right, that's the entire point of the AC generator. Even after half a turn, the red color side is still connected to below, and the blue color side is still connected above. So the sides will always be connected to the same sides. Come, Sanjay, let me test you your right-hand grip rule. Sorry, Fleming's right-hand rule. Do you think the current will flow this way or this way?
Current, is it? Current.
Number one or two?
Current or what?
Yeah, current.
Two.
Two, right? So, because, yeah, Jingwei, you got it. The current is rotating this way, right? Means that the left side is going up. The right side is going down. That's the motion of the coil, right? The left side goes up and the right side goes down. Magnetic field always points from north to south. Using our Fleming's right-hand rule, we'll get like this, right? my middle finger is pointing into the page, which tells us that our current is going into the page. This one is the induced current over here. Right? If we trace this, trace the red color side over here, trace the red color side to here, we can see that the current is flowing like this, and the current is flowing like this. That gives us the output of the AC generator. So the AC generator is going to be like this, and help me draw like half a sine graph. Right, that's the output of the AC generator. Half a turn later, what's going to happen? The left side is going up, the right side is going down, magnetic field is to the right. Always draw the directions first before you apply your Fleming's right-hand rule. Then, Louis, can I ask you, over here the current, right? Do you think the current will flow the same way or the opposite way? Wait, the motion is the same, right? The magnetic field is the same. So the current is still going to flow, or backwards, is it? Oh yeah. But like inside the coil, the current is still going to flow the same way, right? The current is still going to flow like this, flow like this. But now the blue color side is connected to the other side. Right, the blue color side is connected to the other side. So what we notice is that the current going into the output actually reverse direction. Right, the current going into the output reverse direction. That's why when we draw the output voltage, it's going to be a full sine graph like this. This negative part, right, of the voltage, Jingwei, what does it tell us when the voltage becomes negative? Negative direction, right? Means the current what? Opposite direction, right? So when the V becomes negative, it tells us that the current reverse direction every half a turn. Okay, so that's how an AC generator works. Anyone got burning questions of AC generator? All right, next thing is the maximum induced EMF. Which position do you all think the maximum induced EMF will be the maximum? Bro, my iPad keeps, I don't know why like the fridge affects my iPad. You all heard the fridge sound just now? The fridge just like, then my iPad disconnected. Like when the fridge makes that sound. Maybe actually. Okay, wait, let me fix this. Okay, come. When do you think the EMF induced will be the maximum value? Horizontal or vertical? Horizontal. Why? What makes you so sure?
Because it's cutting most of the
It's cutting most of the magnetic
magnetic field lines.
field lines, right? So if we notice over here, bro, I keep getting this stupid ad. So, I mean, obviously you gotta take this, then.
It's possible.
Yeah, it's impossible. No, so like at the horizontal position, right, what do we notice? We focus on, remember, we must focus on the left side and the right side only. Only focus on these two sides. At the horizontal position, can you all see that it's moving up and down? Right, over here is cutting the most magnetic field lines. Cutting the field lines is equivalent to a change in flux. So at a horizontal position, is cutting the most field lines, right? Biggest rate of change of flux. So horizontal position is the maximum EMF induced. How about the vertical position? Am I cutting the field lines? Not really, right? Yeah, but okay, in reality it's like I'm cutting way less, right? Because in the vertical position, I'm moving parallel to the field lines. I'm not cutting any field lines. Do you all see that the bulb is not lighting up? Right, at the vertical position, I'm not cutting any field lines. No change in flux, which means that my induced EMF is zero induced EMF. Take the first worksheet. Nice cut. Prepping for oral. Prepping for oral, is it?
I just took the barber to cut it short and then cut it really short.
You need to turn like 3 times, like don't cut so short. If not, they won't understand one. Alright, so zero induced EMF. Okay. Hey, can I recap first? I forgot to say. What's flux? What's magnetic flux? Yeah. So I have a magnet. I have a coil. The magnet got magnetic field lines, right? Flux is the magnetic field lines that are passing through the coil. This one is called flux. Right? Flux refers to the magnetic field lines that are passing through a coil of wire. Right? So the next thing that I'd like to ask is that what happens when the speed of rotation of the coil is doubled? What happens when I spin it twice as fast? Any idea what is going to happen? Come right here. Speed of rotation, 2x the speed of rotation. What's going to happen to the output graph? Turns more, yeah. So I get what I mean. 2 times the induced EMF and also 2 times the frequency. So if we draw the graph, it's going to be like this, like this, like this, like this, like this. But why you say 2 times the height leh? What makes you so sure? Cause the change in flux is not more. Cannot use more. Cannot use greater. Faraday's law says what? Faster, right? The change in flux is faster. When I spin the thing twice as fast, you can see over here, when I increase the wind speed, I'm cutting the field lines faster. Right? I'm cutting the field lines faster. By Faraday's law, the induced EMF will be bigger. Right? If I slow down, I cut the line slower. Slower change in flux, there will be a smaller induced EMF. Okay, so must know that there's always 2 effects to this. Last thing is transformer. Transformer Vp over Vs equals to Np over Ns. What's N again? Number of turns or coils lah. Right? N is the number of turns in a primary coil. N is the number of turns in a secondary coil. Maybe just write as a note. N is the number of turns. Okay, transformer only got 2 formulas. VPIP equals to VSIS. Actually, what does this formula mean? VPIP. Power is power, right? So this formula tells us that in an ideal transformer, the power in the primary coil, right, because power equals to VI, the power in the primary coil is equal to the power in the secondary coil. In an ideal transformer. Let's say we don't live in an ideal world. Let's say there's a 70% efficient. What do you got to do to this guy?
75% of power from primary is equal to power from secondary.
All right. So if it's not 100% efficient, we must take VPIP times efficiency equals to VSIS. Means that we lost some power. Not all the power go to the secondary side. Okay, so my last question is that something they like to test a lot. It's about power loss in the transmission cables. So, maybe come Cliff. Can tell me, Cliff. Power loss in the transmission cables, what formula do we use? P equals to what? P equals to I square R, right? Power loss in the cables, we must always use P equals to I square R. More specifically, is the what current? Secondary current. Right, we will never use what? P equals to IV, P equals to V squared over R. What's the reason what's the reason I step up the voltage? Like, what's the reason before I send it to the power lines, I step up the voltage? Reduce current, right? Who is it? Reduce current. The current actually reduced. You know why the current reduced?
Because more voltage. It should be the same.
Yeah, the power is the same on both sides. So if I increase the voltage, the current will be smaller. I reduce the current, what happened is that my power loss is actually reduced. So I reduce power loss in cables.
Will this be an actual question?
This one, the power loss. Yeah, it comes out a lot. That's why I have it here. They'll ask you like why, like 2 marks, why did I step up the voltage? So it's to reduce the power loss in the cables. Okay, can So right now we're gonna do the quiz. I'll give you all 12 minutes.